Hi guys, in this video, I'm going to explain what mTLS is, or mutual TLS is, and how it works. The full form of mTLS is Mutual Transport Layer Security. A simple way to remember it is TLS happening on both sides. That's why here I call it TLS plus TLS. Hence, to really understand what mTLS is, we first need to understand TLS. TLS is a protocol used to secure data when it's transmitted over a network. While we often talk about data having 5 or 6 lifecycle stages like create, store, use, share, archive, and destroy, the truth is data can be transmitted at any stage. And TLS steps in any time two systems need to establish or secure a session for that transmission. The most common place you've seen TLS in action is actually in your web browser, HTTPS protocol. And that's what the S in HTTPS stands for. Technically, S originally stood for SSL, Secure Sockets Layer, but it has been replaced by TLS. So next time you see HTTPS, you know it's HTTP plus TLS. Every time you visit a secure website, like your bank or email, your browser uses TLS to create a session connection. And TLS builds an encrypted tunnel between them. So even if someone is monitoring the network, they cannot read or modify the data being exchanged. And TLS does two very important things with our data during transmit. First, encryption, so no one can read or tamper your data. Second, authentication, so you know who you are talking to. Because we need to make sure we are sharing data with the right party, not some bad guys who claim they are our friends. To achieve this, TLS uses asymmetric encryption at first, and after securely agreeing on a session key, it switches to symmetrical encryption. This is because asymmetrical encryption costs more, both time and energy, and it's relatively slow compared to symmetrical encryption. So TLS combines the strengths of both. With TLS, once we bootstrap trust using asymmetrical encryption, we switch to symmetrical encryption for speed. So, how do asymmetrical encryption and symmetrical encryption work? First, let's check the easier one, symmetrical encryption. Here, let's see an example. Tom wants to send Jerry a message. So first, he encrypts his message using a secret key. This encryption will turn his original message into something looks like this, a ciphertext, an encrypted message. So if a hacker sees this ciphertext, they have no idea what the real message is. Then, after Jerry's computer uses the same secret key and runs the decryption algorithm, he can see Tom's message. So in short, symmetrical encryption means both sides use the same secret key to encrypt and decrypt the message. However, there is one big issue. How do they share the secret key in the first place? If Tom generates the secret key, how can he send it to Jerry safely? If he just sends the key along with the first message, anyone listening on the network could steal the key, and once they have it, they can decrypt every message. This is exactly what a man-in-the-middle attack looks like. A hacker secretly intercepts the communication, grabs the key, and silently reads or even changes the message without either side knowing. This is why we use asymmetrical encryption. Asymmetrical encryption allows Tom and Jerry to securely exchange a shared secret, even if someone is watching the network, without ever directly sending the key. So how does asymmetrical encryption do that? Asymmetrical encryption uses two different keys, a public key, which is shared openly, and a private key, which is kept secretly, known only to the owner. These two keys form what's called a key pair. Now let's see how asymmetrical encryption works exactly. Back to our Tom and Jerry scenario. Let's see how they could use asymmetrical encryption to communicate securely. Step 1. Jerry first needs to create a key pair, one public, one private. Step 2. He shares this public key with Tom, and this public key is safe to share to anyone. Step 3. Tom takes Jerry's public key and uses it to encrypt the message. Step 4. Tom sends this encrypted message to Jerry. Step 5. Jerry uses his private key to decrypt it. Now, here is the key takeaway. Only Jerry's private key can decrypt what was encrypted with his public key. So even if a hacker on the network intercepts the message, it's totally fine. They can't decrypt it without Jerry's private key. And that private key is stored securely with Jerry and never gets shared, not even once. So hacker can only get a ciphertext, but they cannot crack. The secret key has never been shown up in the network. It's stored with Jerry locally only. This is the beauty of asymmetrical encryption. Tom and Jerry did not need to secretly meet to share a password. Tom just needed Jerry's public key, and that alone was enough to send a secure message. Now at this point, you might be wondering, wait, why we can share public key with anyone? If the public key and private key are related, can hackers in the middle just use brute force or math to figure out the private key using public key? That's a great question. And the answer is no. You cannot brute force private key using public key. Asymmetrical encryption is uncrackable. It's computational infeasible. Now let's see why. It's because asymmetrical encryption rely on one-way math functions, which means the functions are easy to do in one direction, but almost impossible to reverse. Here I say one-way math functions are almost impossible to solve. That's because the math can be reversed in theory, but not in practice. Unless something huge changes, like a math breakthrough or powerful quantum computers, with today's technology, solve one-way math function would take thousands or millions of years, and it would cost more energy than Earth has ever produced. It would cost more memory that ever exists on Earth. And why is that? I'll explain soon. So now you know the beauty of asymmetrical encryption. You know how safe it is. Here are some common asymmetrical encryption algorithms. As you can see, all asymmetrical encryption need a key pair, but they are built on different one-way functions. Now, Let's take RSA encryption as an example and figure out how its one-way math function works. RSA encryption is the most widely used asymmetrical algorithm, and the one-way math function it's based on is factoring large prime numbers. Let's see how RSA works. Step 1 in RSA encryption. Pick two very large prime numbers, P and Q, randomly. And here to show clearly, we pick these two large numbers for demonstration. But in real case, the two large prime numbers picked are much bigger. They have a binary length of 1024 bits, which is something like this. 1024 digits of zeros and ones, which is 308 digits long in decimal. It's a number between 10 to the power of 308 and 10 to the power of 309. By the way, P and Q don't have to be exactly the same length, but in practice, they are chosen to be very close in size to make N for next step the desired total size, which is 2048-bit modulus. Okay, now let's see step 2. Multiply these two prime, P and Q, to get a number N. This N is easy to create by multiplying, but extremely hard to factor backward, and RSA's security relies on the difficulty of factoring N back to P and Q. We said this N will be 2048-bit long because 2048 is impossible for hacker to crack, and also fast for encryption and decryption for us, so it's a good balance. Step 3. Compute Euler's quotient, phi of n. Phi of n is crucial to find our private key. We'll see why shortly. Step 4. Choose the public exponent e. E should be smaller than phi of n, and it needs to be a prime number. Normally, here we choose e equals to 65537 because this number is not only a prime number, it has only 2 1 bits in binary, so the computations will be faster. Step 5. Compute the private key. We're looking for D here, and the relationship between D, E, and phi of n satisfy this equation, which is multiply E by D, then divided by phi of n, and the remainder must be 1. I'm sure you have noticed. If we try get D that satisfying this equation, there will be many. You're correct. So here, we always use the smallest positive one. Okay, now we have both public key and private key. As you can see, public key is n, e, and private key is n, d. They're not one number, but parameters to a function. Step 6. Encrypt a message using public key. Let's encrypt a small message, like the number m equals 1, 2, 3, 4, 5, 6. We know all messages, all information in computer science, in computer, and numbers, zeros and ones in binary. So if the message m is this, the final ciphertext, the encrypted message c will be m to the e mod n. And step 7. When the receiver gets the ciphertext, he can decrypt the message with private key. M equals c raised to the power of d, modulo n. And in Tom and Jerry's case, only Jerry having the private key can do this. And again, let's do a quick computation to see why factoring n a 2048-bit RSA key is impossible. Here, this is the most efficient algorithm for factoring large numbers in the world right now, GNFS. And the best supercomputer for human being now can do 10 to the power of 15 operations per second. To factoring a 2048-bit RSA key, we need 5 times 10 to the power of 33 operation. Let's say if a hacker has both the best supercomputer and the best algorithm, he still needs 10 to the power of 16 seconds, which is 371 billion years to solve. Say no more. You can see how difficult it is. It is impossible. Okay, now we're clear with what is TLS, what is symmetrical encryption, what is asymmetrical encryption, and what is RSA encryption algorithm. Now let's take a step back to Tom and Jerry's case to see what mTLS is. In mTLS, both Tom and Jerry generate their own key pairs, a public key and a private key. Then step 2, they exchange their public keys, and then they both use each other's public key to encrypt the message so they can decrypt the message received using their own private key, like in this demonstration. How do you think this? Is this true? No, this is not how mTLS really works. Although we surely can use asymmetrical encryption like this, but remember, use asymmetrical encryption is way too slow for large messages like web pages, files, videos. So Tom and Jerry only need to do asymmetrical encryption once. They use their private key to prove their identity, and then use each other's public key during the handshake to establish a shared session key. Let's see how real mTLS works. Step 1. Both Tom and Jerry will need to generate their own key pair. And then step 2, they will exchange their identity. This identity not only has their public key, but also has other information, like expiration date. This is a certificate. And then step 3, they will send digital signatures to each other to prove they own the private key. Each side proves their identity by signing with their private key. The other side checks the signature using the public key from the certificate. If the signature is valid, it proves they really own the matching private key, and that identity in the certificate is real. Remember, in asymmetrical encryption, a private key is used to sign, and the public key is used to verify that signature, which means only the real owner of the private key could have created that signature. This process has also involved with a certificate authority, which belongs to a PKI, a public key infrastructure. That's another component to support identity, but not our key focus in this video. So after Tom and Jerry prove their identity by exchanging certificates and verifying their signature, they still need a shared secret for symmetrical encryption. And here, step 3.2, mTLS, use another one-way math function to build the shared secret for this session. Let's be clear. Although I marked them as two steps, step 3.1, step 3.2, but these two steps are happening at the same handshake. This ECDH is another key agreement protocol. Both Tom and Jerry will generate a temporary code and put it in their identity. So when they receive each other's identity, they verify the identity using the private through the network. Using the private key, asymmetrical encryption. If valid, they use this ECDH code to build a shared secret together. But this shared secret is never sent through the network. They only send one part of it to each other. I will explain this in next slide. For now, we know they have the same secure shared secret, and they have identified each other. Then the rest steps are very straightforward, just a common symmetric encryption process. Both Tom and Jerry can use the same shared secret to encrypt and decrypt. Now let's see how Tom and Jerry build the shared secret. This is the protocol they build the secret together. Elliptic curve Diffie-Hellman key exchange. First, they both agree on a public starting point called G, capital G. This G is a fixed point on a special elliptic curve. It's public and everyone knows it. Now, Tom secretly picks a random number, A. This little a is Tom's ephemeral private key, used only for this session. But both Tom and Jerry's private key, public key, the key pair we mentioned before, they are used for long term. But for every session, they're gonna use this ephemeral private key. So Tom multiply little a by G and gets a new point called big A. So big A equals A times little a times big G. And Tom then sends big A to Jerry over the network. So big A is just like big G. They might be received, they might be seen by hacker, but that doesn't matter. I'll tell you later why. So meanwhile, Jerry does the same thing. He picks his own random number, little b, which is his private key for this session. He also multiplies it by G and gets a big B, a capital B. Big B equals little b times capital G. So Jerry sends this capital B to Tom. Now both Tom and Jerry have each other's public points, big A and big B. And they still have their own private number, little a and little b. Here comes the magic. Tom used little a and Jerry's capital B to compute the shared secret as A times B. At the same time, Jerry used little b and Tom's capital A to compute the same thing, S equals B times A, because in both equations, S equals little a times little b times capital G. So they have same shared secret. The key point here is the shared secret S was never sent over the network. It was built independently by Tom and by Jerry, using math, not messaging, not network. So even if a hacker sees big G, big A, big B, he still does not know little a and little b. If he wants to recover them from a equals little a times g or b equals little b times g, means he need to solve a elliptic curve discrete log problem, which is also computational infeasible. This is also a one-way math function, so this will take billions of years. Okay, so that's the whole process of mTLS. The key of mTLS is asymmetrical encryption, and the key point of asymmetrical encryption is one-way math function. So you are clear with the whole process, and if you have any other question about mTLS, TLS, asymmetric or symmetric encryption, please leave a comment. Thank you for watching. See you in the next video.